Okay, please feel free to interrupt me anytime. Okay. So basically what I'm going to do today is mostly sample problems, solving sample problems. Okay. But before doing that, I'd like to discuss the concept of complex power. Okay. So in the previous relationships that I described last meeting, all the quantities that we were dealing with were scalar quantities. They were not complex numbers. They were just scalar quantities. Now, there's a way of determining the real power and the reactive power to a particular circuit using this concept of complex power. But in this case, you're going to have to go back to complex mathematics. Okay, complex power is defined as follows. No? If we have an element, and this is the voltage across your element, and this is the current through your element, your complex power S is defined as your voltage multiplied by the conjugate of your current. Again, no, that's the voltage multiplied by the conjugate of your current. And it's very easy to show that. So if I perform this complex operation, okay, V at an angle theta V times I at an angle minus theta I. So we multiply the magnitudes and then we add the angles. So I'm going to get VI at an angle theta V minus theta I. So this is in polar form. If I convert this to rectangular form, okay, how do you convert that to rectangular form? The real part is VI cosine theta V minus theta I. And the imaginary part is VI sine theta V minus theta I. But if you will recall from our previous discussions, VI cosine theta V minus theta I, this one, is actually equal to P. And this one is actually equal to Q. Thus, S, complex power S, is just P plus JQ. In other words, if we evaluate this product, we pick out the real part, and that's equal to your real power, and you pick out the imaginary part, and that's equal to your apparent power, or your VARs. Note that this is a complex number. However, this is not a phasor. No? Not a phasor. So we said we only use the vector sign on top to denote phasor. No? But the reason why we do this for complex power is because if you just say S is just volt amperes. No? This is your volt amperes. So if you recall from our discussion last week, this is just the RMS value of your voltage multiplied by the RMS value of your current. No? On the other hand, S, okay, this is your complex power. No? This is P plus JQ. So this is an exception whereby we put the vector sign on top of the S, even if this is not a phasor, so that we can differentiate it from your volt amperes, which is just V times I. Any question with regard to this? Any question? Okay, so we're still okay. So I summarize again the power equations. Okay. So if you remember this particular slide, then you should be okay for calculating power in AC circuits. So you have real power in watts. If you know the voltage and the current, if you know the phasor voltage and the phasor current associated with your element, then you compute the power in watts as VI cosine theta V minus theta I. If that is a resistor, then the power in watts is just I squared times R, where I is the RMS value of your current. And then the reactive power, again, if you know the phasor quantities, you use this formula. If you know the RMS value of the current, For an inductance, it's I squared XL. For a capacitance, it's negative I squared X of C. So remember that the reactive power or the VARs of a capacitor is always negative. And then this is apparent power S. So this is what I mentioned earlier. S is equal to your volt ampere. So this is just the RMS value of voltage multiplied by RMS value of current. Then you have your power factor, which is P over S. That is in effect cosine theta V minus theta I. And when you give the power factor, you should specify whether it is lagging or leading. Lagging or leading depends on the relationship between the current and the voltage. It's always with respect to the current. If the current lags the voltage, it's lagging. If the current leads the voltage, it's leading. And then here is where you can deal with power using the complex power formula. Just as an anecdote, no, in my time, we tended to use these formulas nung panahon ko because we didn't have complex calculators, no? Complex math calculators. When we did complex math before, we had to do everything manually. But now that you have complex math calculators, it's not so bad to work in the complex domain. So you can use the complex power formula. Okay, then I mentioned this also last time. This is as an aid to remembering the relationships. No? You just remember this triangle. We call this the power triangle. This is a right triangle. The angle is the phase angle between your voltage and your current. So that's theta B minus theta I. Okay? That's your angle. Okay. If you get this, the base of the triangle is your real power, and take note that is just S multiplied by cosine of theta. S multiplied by the cosine of theta. The height of your triangle is your apparent power or your VARs, and that's S multiplied by the sine of theta. Okay, so that's consistent with this because remember that VI is equal to S. VI is equal to S. So dito nakikita nyo, P is S cosine of theta. That's theta B minus theta I. And Q is S sine of theta. Ito pala, no? S is equal to VI. No? I didn't have to rewrite it. Sorry. Okay. From the power triangle, if we know P and Q, you can compute for S. No? If you know P and theta, you can compute for Q. No? As a matter of fact, if you know any two quantities in this triangle, no? So there are four quantities here. If you know any two quantities, you can compute for the other two. Okay. So what? For example, no, if I know P, no, if I know Q and theta, I can compute for P. No, P is equal to Q. Okay, arctangent of theta. No, if I know Q and theta. Of course, theta. If you know P and Q, you can compute for theta. Okay, theta is the arctangent of Q over P. So anyway, all I'm saying is this is all you have to remember, no? And you can practically derive all of these quantities. Okay, remember also that here, this Q, you have to make this negative. No? Make Q negative if PF is leading. This is very important. No? This is where students sometimes make a mistake. They forget to make Q negative if the PF is leading. Okay, so let's go to our examples. No? So this is first example, rather simple example. In the circuit shown, V of t is equal to 311 cosine 377t. So the problem is to find the power and the reactive power delivered to the load. Find the power and reactive power delivered to the load. Okay, so always as a first step, no, you transform the circuit. Okay, so what is our transformed circuit? Okay, you have a voltage. You have a voltage source this way, and then you have a Z1, and then you have a Z2. Okay, let's say this is L1, and let's say this is L2. Okay, so Z1 is 0.5, okay, plus J. Omega is 377, no? So omega is equal to 377. So this is J 377 multiplied by 3.06 M. 3.06 M. And if you compute for that, okay, this is going to be 0.5 plus J 1.154. This is in ohms. And Z2 is equal to 7.5, okay, plus J, again, this is omega 377 multiplied by 12.854 M. And this is going to come out 7.5 plus J 4.846 ohms. Okay. On the other hand, V, the phasor equivalent of our source, is going to be 311 over the square root of 2 at an angle 0, which is actually just 311 over the square root of 2, no, in rectangular form. Because if it is at an angle 0, that means there's only a real part. And so the real part is just 311 over the square root of 2. No? In other words, in rectangular form, this is 311 over the square root of 2 plus J0. Okay, any questions? Any questions with the transformed circuit? Okay. So what do we want to do? No, we want to get the power and reactive power delivered to the load. So this is my load. Okay, let me assume that this is my load voltage, V sub L. No? And let me assume also that the current that flows here is I. No? So remember, V sub L and I will also be phasors. So first, let me determine I. No? Okay, I. Okay, this is going to be equal to V over your total Z. No? So V over Z1 plus Z2. No? That is the total Z with respect to the terminals of your voltage source. That's equal to I. So what is my Z total? Oh, well, first of all, V, no? V is 220 over the square root of 2. Tama ba? Sorry, 311. Sorry about that. Sorry. So V is 311 over the square root of 2. And then Z1 plus Z2, if I get Z1 plus Z2, that is actually 8 plus J6. No? Because 7.5 plus 0.5 is 8. 4.846 plus 1.154 is equal to 6. So this is equal to 8 plus J6, which will give me, okay, so this is, I computed this already. This is 22.0 at an angle minus 36.87 degrees. This is in amperes. No? Don't forget your units, amperes. So that's equal to I. If I know the value of I can determine the value of V's of L. No? V's of L is just equal to I multiplied by Z2. I multiplied by Z2. So this is just 22.0 at an angle minus 36.87 degrees. And my Z2 is 7.5 plus J4.846. Okay. So ito, I hope you've had enough practice by now. Okay. Pinipindot-pindot lang nyo yan sa calculator ninyo, no? And you're going to get V's of L after entering this in your calculator. Okay, this is going to be equal to 196.45 degrees. Sorry, 196.45, not degrees, no? At an angle minus 4.0 degrees. This is in volts. Okay, by the way, V's of L can also be obtained by voltage division, no? By voltage divider. V's of L would be equal to V Z2 over Z1 plus Z2. So you could also have used that particular formula. No? So that's just indicative of many ways of doing things. No? So I know now my current flowing through the load. I know the voltage across the load. So my complex power S is now just equal to my voltage multiplied by the conjugate of my current. The conjugate of my current is just definition of conjugate, no? That is the mirror image of your phasor mirrored along the horizontal axis, no? So what does that mean? Either you make the imaginary part negative or you make the angle negative, no? So my voltage is 196.45 at an angle minus 4.0 degrees. And my current here, the conjugate of my current, this minus 36.87 will become positive. So this is now 22.0 at an angle 36.87. Yun yung conjugate. And if I do that, okay, this is going to be equal to 4321.8. Okay, at an angle, well, you can see the angle, no? You just subtract from 36.87 4 degrees. So this is going to be 32.87 degrees, which will give me 3630 plus J 2346. Okay. This is SL, no? The complex power across my load. So pag nakuha ko yan, alam ko na that this is my piece of L. Alam ko na rin that this is going to be my Q's of L. No? So piece of L will just be 3630 watts. The Q's of L will just be 2346 bars. So this is my answer. So this is using complex power. Any questions? Any questions? How about you, Carl? Any questions? Okay. Alternate solution, no? Like I said, nung panahon namin, we didn't like doing complex calculations because we didn't have complex number calculators, no? So we always wanted to do things in the simplest possible way you would be able to do it manually, no? So, for example, what is an alternate solution? At this point, no, at this point, dito, I already know I. No? I know that I is equal to 22.0 at an angle, what is it? Minus 36.87 degrees. No? This is in amperes. No? Which means that my RMS value for I, so that's just I, no? This is the magnitude of my phasor I, which is the RMS value, no? RMS value of I. What is this equal to? This is equal to 22.0 amperes. Okay, if I want the power delivered to the load, I know that real power will only be delivered to a resistor. Real power will only be delivered to a resistor. Therefore, right away I can say piece of L is just I squared R's of L, or 22 squared multiplied by 7.5 ohms. Because this is 7.5 ohms. And I'm going to get the same answer. I'm going to get 3630 watts. And Q's of L, I know that reactive power will only be delivered to either an inductance or a capacitance. In this case, it's an inductance. Okay. So this is going to be equal to I squared times my load reactance. So this is going to be 22.0 squared. My load reactance is this, no? 4.846 ohms. This is the reactance of my load. Remember, Z2 is my load. No? 4.846. And this will give me 2346 bars. Okay? So, in other words, dito lang tayo nag-compute ng complex number. Pagkatapos nun, yung subsequent computations are no longer involving complex algebra. So it's up to you what method you use. If you like doing complex calculations, you can use this method. Or you can use this method if you don't want to do complex calculations. Any question? Any question? Okay. Okay, here's a second example. Okay, I have this circuit. I'm given this voltage in time domain, 200 cosine 10t. Then I'm given the circuit parameters, in resistance and inductance. So the problem is to find all real and reactive power. Lahat ng real at saka reactive power associated with this circuit. So as usual, we first transform the network into the frequency domain. I'm not going to go through that anymore. No? We know that omega is equal to 10, right? And therefore, what is going to be the impedance of this? No? This is going to be 1.2 times 10. That's the reactance. So this is J12. No? Okay. On the other hand, this is 0.5. So 10 times 0.5 is 5. No? That's your reactance. So this is J5. And then this is 0.01. No? 0.01 times 10 is 0.1. You get the reciprocal of that. Okay. So that's 10. And so this is minus J10. No? Now, what about my voltage? My voltage is just 200 divided by the square root of 2. Okay, my phase angle is equal to 0. So this is 141.42 at an angle 0. Or if you convert this to rectangular form, it's really just 141.42. So this is now my transformed circuit. Now, we had this example last time. We want to determine I1, I2, and I3. And we showed that there were many ways of doing this. One way was to use circuit simplification. So you get the total impedance seen by the voltage source. And then you can solve for I1. And then after solving for I1, you can use current division for I2 and I3. No? The other way of solving this is the node voltage method. No? You define this as a node voltage, this as your reference, and then you write your nodal equations. You're going to be able to solve for this node voltage. No? You'll be able to solve for this node voltage. And once you get this node voltage, you can now compute for I1, I2, and I3 from the node voltages. Okay, so I'm not going to go through that anymore. You should have had enough practice doing that. And these are the answers that will come out. No? The value for I1, I2, and I3. Okay, what does this mean? No? This means that 7.071 is the RMS value of I1. No? 10 is the RMS value of I2. 7.071 is the RMS value of I3. Okay. We can get the power delivered to R1. This is R1. That should just be the RMS value of I1 squared times 6. So this will be I1 squared times R1, no? Or 7.071 squared times 6. Okay. And if I do that, okay, this is going to be equal to 300 watts. Okay, I do the same thing, no? The power delivered to R2 is going to be the RMS value of I2 squared times R2. Okay. Again, no, very important. These are scalar quantities. Huh? These are not complex numbers. Hindi walang vector sign sa taas, no? So I1, let me just note that here, no? I1 is the RMS value of I1, no? I2 is the RMS value of I2 and so forth, no? That's why importante, no? You have to indicate whether the quantity you're working with is a complex number or not. No? Okay, so anyway, what is this? This is going to be 10 squared multiplied by R2. R2 is 5 ohms. So this is 500 watts. Any other element which will consume real power? Wala na, no? Remember that real power is only delivered to resistances. So there are only two resistances in the circuit, so there's no other element where real power will be delivered. So the remaining elements, L1, L2, L3, you only will have reactive power. So what is QL1? That's reactive power delivered to L1. That's I1 squared times XL1. Okay, so that's 7.071 squared. What is XL1? XL1 is 12 multiplied by 12. And that will give me, I have it somewhere here, no? 600 VARs. Okay, and then the reactive power delivered to L2 will be I2 squared times XL2. That is 10 squared. What is XL2? XL2 is 5 times 5, no? Which will give me 500 VARs. Okay, meron pa isa, no? The reactive power to C, so ito yung C, okay, hindi naka-label, no? Let's just call this C. The reactive power to C is going to be I3, no, not the phasor, no, the magnitude of I3 or the RMS value of I3. So this is going to be I3 squared X of C. Now you have to make this negative, because C is a capacitor. The reactive power delivered to a capacitor is always negative, no? So importante ilagay niyo itong negative sign dyan. So this is going to be 7.071 squared times 10. Okay. And what will that be? That will give you minus 500 VARs. Okay, so we now know the power or reactive power delivered to all of the elements, no? What about the source? What about the source? Okay. The power and reactive power, okay, associated with the source, you can use the complex power formula. Okay, S is equal to V multiplied by I1 conjugate. Okay. So this is going to be 141.42 at an angle of 0 degrees. Okay, what is the conjugate of I1? The conjugate of I1 is 7.071 at an angle 36.87 degrees. Okay, and if you solve this, what you're going to get is see, no? Yeah. What you're going to get is 1,000, okay, at an angle 36.87 degrees, no? You multiply this by this, that's 1,000, and then you add the angle, 0 and 36.87 is 36.87 degrees, which is equal to 800. If I convert this now to rectangular form, this is 800 plus J 600. This is volt amperes. The unit for S is volt amperes. But I know that this is my P and this is my Q. No? So for my source, so for the source, let me just call this S, no? As, complex power of the source. P of S is 800 watts and Q of S is 600 bars. Any questions so far? Any questions? Carl, can you give me a thumbs up kung wala kang if you have no questions? Okay, good. Okay, from the directions of current, no? Nakikita natin yung directions of current dito. Is the source absorbing or delivering energy? Can I ask? So, shout out lang, no? Kung yung sagot. Is the source absorbing or delivering energy?
Delivering po.
Yeah, delivering, di ba? Kasi kung yung current is flowing out of the positive terminal, no? Parang DC, di ba? If the current is flowing out of the positive terminal, that means as it is passing through the source, the charges that constitute the current is gaining energy. No? Is gaining energy. Right? Therefore, this is delivering power. Okay? So this is the source is delivering. On the other hand, we know that these are active elements and they will be absorbing. No? Now there's your law of conservation of energy. In this case, we split this into two. No? The total real power generated should be equal to the total real power delivered. No? Delivered. And then the total reactive power generated should also be the total reactive power delivered. Okay, so from here, the total real power generated, this is generated by the source, is 800. Okay, so that's PS, no? Let me put it in equation form first, no? The total real power generated is PS. That can only be delivered to resistances, no? So that can only be delivered to R1 and R2. So this should be equal to PR1 plus PR2. And tama, no? 800, this is 800, is 300 plus 500. So this is correct. So naman, the total reactive power generated should be equal to the reactive power delivered to L1 plus the reactive power delivered to L2 plus the reactive power delivered to C. No? Because it's only your inductances and capacitances which will absorb reactive power. No? So that would be the sum of these three. No? So let's look. No? 600, tama, no? If you sum these three, that's equal to 600. So ito 600 is equal to 600 plus 500 minus 500. So tama siya. So that's the law of conservation of energy. Okay. Now, what's nice with this example is if you take out this capacitor, if you remove the capacitor, ito tatanggalin mo, you're going to notice that I1 will increase. Right? I1 will increase. Okay, why? No? Because Q's of S will be larger. Right? Kasi mawawala itong Q's of C, no? Kita nyo itong term na to. Ito mawawala, ito negative, no? The value of that is negative. This will disappear. So your Q's of S will be larger, no? It will be QL1 plus QL2. You have the same piece of S, you have a larger Q's of S, no? Your S of S, which is equal to your volt amperes, no? This is your volt amperes of S. This is the square root of Q's of S squared plus Q's of S squared. This will also be larger, right? If your voltage is the same, if the voltage is the same, if your volt amperes is larger, this means this is I1, will be larger. I1 will be larger. So, putting this capacitor here actually allowed us to reduce the current that is being supplied by the source. No? That sounds a little maybe strange at first, no? Seemingly strange at first kasi dinagdagan natin ng element dito, lumiit yung current. No? And that's what we call, no? So the capacitor, in effect, no? The capacitor causes I1 to decrease. And this is what you call, we have a term for this, this is what you call power factor correction. That's what you call power factor correction. Okay, pag minsan, may makikita kayong advertisement of power saving device. Have you ever encountered that, no? They sell these power saving devices. You plug it to your outlet and pinapangako ng mga vendor na makakatipid ka sa kuryente. Have you heard of those? Either of you? Okay. Actually, pag binuksan mo yon, all it is really is a capacitor. No? And what it really does is it really just tends to make the current supplied by Meralco smaller. Because if you have a capacitor, as I pointed out here, no, it tends to make the current supplied by the source smaller. But actually, those power saving devices achieve, maybe for a house, achieve not that big savings. Sometimes, yeah, but maybe not that big savings. So ngayon, pag nakita nyo yung power saving device, alam na nyo, no? Baka capacitor lang yun sa loob. Sa mga poste ng Meralco, pag minsan meron silang linalagay na capacitor. Because if the load is heavily inductive, which is usually the case, most industrial loads are inductive, then it will be helpful to put a capacitor across your load so that your total Q becomes smaller and then the current will become smaller. So that's just some insight for you, no? Additional insight for you. Any question with regard to that? Did you understand that concept? Okay. Okay. Now this is a typical, next example, no? This is a typical problem that you encounter in real life, no? Because these are the type of problems that electrical engineers normally encounter. In other words, sa totoong buhay, it's not very often that you're asked to solve for phasor voltages or phasor currents. Usually, sa totoong buhay, what you're faced with are electrical loads, which are specified in terms of kilowatts or volt amperes, watts or volt amperes. and you want to know what your total current is going to be. So this is that typical problem. I have a voltage source, probably my Meralco voltage, 220 volts. I have 4 loads connected across my source. So this can be my household appliances, or this can be my factory loads. No, in this particular case, pala, it's an industrial shop. No? So this is an induction motor. This is an electric heater. These are my lights, my total lighting load, and this is my total outlet load. And what I want to do is I want to find the total current that needs to be supplied by my utility provider. In this particular case, maybe Meralco. No? Or if this were a generator, I want to know what the total current my 220 volt generator has to supply. Okay, so do you understand the scenario here? Okay, so here we're going to assume that the wires that supply voltage to my load has zero resistance. No? In other words, these wires are ideal. No? In the real world, actually, may resistance and inductance yung mga wire na yan. No? Okay, so let's go ahead and solve this problem. Okay, so let's do it. One load at a time. No. So what I want to do is I want to compute for I1, I2, I3, I4, and then I of t will just be the sum of these 4 currents. Note that this is KCL. You perform KCL on the phase source. No? Because I could have gotten the RMS value of I1, I2, I3, I4, but I cannot add RMS values together. It's not going to give me the total RMS because of my angles. I can only add phasors together. Again, that's a common mistake of students. No? They get the RMS values of the currents and they add it together in a KCL. Hindi pwedeng ganon. No? Kailangan nakasama yung angle. No? So anyway, I'll work with each load separately. No? So let's first consider load 1, L1. Okay, I know that my power, let me call it P1, is equal to 2000 watts. My power factor is 0.85 power factor lag. Here, no? 2000 watts, 0.85 power factor lag. I can compute for Q1. No? Again, you can use your power triangle, right? If you don't want to memorize formulas, you can use your power triangle. This is going to be P1. This is going to be Q1. I know that this theta is equal to the arc cosine of 0.85. No? That's a value of this angle, the arc cosine of 0.85. But I can compute for Q1, no? Because the tangent of theta is just Q1 over P1. No? So if I multiply P1, no, by the tangent of theta, that's equal to Q1. No? So that's 2000 times the tangent of arc cosine of 0.85. Because theta is arc cosine of 0.85. And if I compute this, this is 1,240 bars. Okay, what I'm going to do is, itong 220 volts, this has no phase angle. I'm going to assign this as my reference phasor. Take note that 220 volts here is already the RMS value. No? Ito, no? RMS value yan. In other words, this voltage is going to be 220 at an angle 0 degrees. No? So if I'm not given any phase angle, I can assign any phasor in the circuit to be my reference phasor. So in this case, I make 220 my reference phasor. I assign that 0 degrees. And then I'm going to compute for the angles of I1, I2, I3, I4, all with reference to the reference phasor. Okay, I know that, okay, P plus JQ in this particular case, ano? P1 plus JQ1, that's my complex power. That should be equal to V, oh, this is V. That should be equal to V. Ito naman, this is the phasor V. No? That should be equal to the phasor V multiplied by I1 conjugate. No? The conjugate of this particular current. No? So I can compute now for I1 conjugate, which is P1 plus JQ1 over V. So this is going to be 2000, this is going to be 2000 plus J1240 all over 220 at an angle 0. And I'm going to get I1 conjugate is going to be 10.7 at an angle 31.79 degrees amperes. Therefore, I1 is 10.7 at an angle minus 31.79 degrees amperes. Any question how I got that? So I just use the complex power formula. Okay. Could I have solved for I1 in a different way? No. Yes, no? The answer is yes. No. Why? This is S1. No, this is S1. S1 is equal to the square root of P1 squared plus Q1 squared. No? Alam ko na yung P1 dito. Alam ko na yung Q1 dito. Okay. So I can now compute for S1. No? I don't have that in my notes, no, because I just thought of this now. No? But let me do it. Okay, this is going to be 2353 volt amperes, not volt amperes reactive. No, S is volt amperes. But this is going to be equal to the magnitude of my voltage multiplied by the magnitude of I1, no? Or the RMS value of my voltage multiplied by the RMS value of I1. So I can solve for the RMS value of I1. That's 2352 divided by 220. And expectedly, I should get 10.7 amperes. But this is just the RMS value. What is my angle? Okay, I have to compute for, theta V minus theta I is going to be equal to R cosine 0.85. That's theta V minus theta I is going to be equal to R cosine 0.85. No? So that's going to be sorry. Yeah, this is going to be 31.79 degrees. Okay. Since theta v is equal to 0, right? Because here, no, theta v is equal to 0, then theta I should be equal to minus 31.79 degrees. Therefore, putting these two together, no, I1 is just 10.7 at an angle minus 31.79 degrees amperes. So notice these two are the same. So again, I'm just illustrating there are many ways of solving for the quantities you need. No? In this case, I used complex calculation, which is very easy with my calculator. No? In this particular case, I did not use any complex calculation. No? I just solved for S1, which is the square root of P1 squared plus Q1 squared. From that, I could compute now for I1. And then the only thing, if I wanted the phasor value of I1, I just have to compute for my angle. And I can do that using this triangle, no? Computing for the angle. Okay, so that's L1. No? Medyo, I didn't realize the pace was so slow. No? Okay, so alam ko na itong I1. Okay, I still need to determine I2, I3, and I4. So let's go to L2. So let's do this a little bit more quickly, no? So for L2, P is equal to 3,000 watts. Your power factor is equal to 1. Pag 1 yung power factor natin, this is P2, no? Pag 1 yung power factor natin, ang ibig sabihin nito purely resistive. Okay? So pag purely resistive, wala tayong imaginary component sa L2. In other words, I can now compute for sabihin natin I use the complex power formula, no? S2 is just equal to 3,000, no, plus J0, okay, which is equal to 220 at an angle 0 multiplied by I2 conjugate, no? So I2 conjugate is 3,000 plus J0, no? So 3,000 over 220, and this will give me 13.64 at an angle 0 degrees, no? Which is also equal to I2. Because if I make 0 negative, it's still 0, no? So that's equal to I2. So ito na yung value ng I2 ko. Okay? So again, note, no? Here Q2 is equal to 0 dahil unity power factor. Okay, let's consider load 3. Okay, P3 is equal to 500 watts. Ano nga ba yung load 3? Ito, no? These are your lighting. Okay, your power factor 3 is equal to 0.9, lagging pa rin. This is lagging. Okay, so again, no, we use the same method. Q3 is equal to 500 tangent of arc cosine of 0.9, no? You'll get used to this formula soon. So this is 242 vars. Okay, I3 conjugate is, this is my real part, 500, plus J, 242, my imaginary part, divided by V. No? V is 220 at an angle 0. So I'm going to get I3 conjugate is 2.52 at an angle of 25.84 degrees. So that will give me I3 is 2.52 at an angle negative 25.84 degrees. Don't forget that this is in amperes. Okay. Finally, for load 4, okay, again, very quickly, no? So this is P4, this is 1000 watts. PF4 is equal to 0.95 lag. Okay, Q4 is just P4 tangent of cosine to the -1 of my power factor. I just give this to you. This is 329 bars. And again, computing for I4 using the same technique previously, I'm just going to get 4.78 at an angle of -18.19 degrees amperes. Okay. Yung Q3 and Q4 are positive because your power factor is lagging. If your power factor is leading, Q3 or Q4 should be made negative. Just remember that. Again, that's where a lot of students make a mistake. No? Nakakalimutan nilang gawing negative itong Q kapag yung power factor hindi lag, kapag yung power factor is leading. So finally, sabi natin, pwede tayong mag KCL, no? Alam na natin yung phasor values of I1, I2, I3, I4, pwede na tayong mag KCL. Is of t is just I1 plus I2 plus I3 plus I4. And if I do this, again, just using your calculator, you're going to get 30.66 at an angle of -15.55 degrees amperes. No? And the RMS value of I of t is 30.66 amperes. Okay. Now, is there another way of solving this problem? Let me just describe an alternate solution. Alternate solution. So, sabihin natin ayokong ayokong mag-phasor addition dito. What could I have done? Okay, let me construct a table. Okay. What I want to do is ganito, no? Okay, this is L1, L2, L3, L4, and this is my total. And I just want to do P and Q here, no? Power and reactive power. So for L1, P is 2000, Q is 1240. For L2, P is 3,000 and Q is 0. Okay, for L3, P is 500 and Q is 242. And for L4, P is 1,000 and Q is 329. Now this total will be the P and Q delivered by the 220 volt source, because of the law of conservation of energy. And if I total this, 2,000 plus 3,000 plus 1,000 plus 500, this is 6,500. Okay, this is watts. And this is 1,811, this is bars. Okay, by law of conservation of energy. Okay. So I have now my triangle. This is for my source. So this is for my source. No? This is my S total. Okay, this is P total, which is 6,500. This is Q total, which is equal to 1,811. No? And this is going to be my theta, which is theta V minus theta I. What is S total? That is the square root of P total squared plus Q total squared. That is for my triangle. And if I compute that, this is 6,474 volt amperes, which is equal to the RMS value of my voltage times the RMS value of my total current. RMS value of my voltage times the RMS value of my total current. So the RMS value of my total current is just going to be 6,474 divided by the RMS value of my voltage. And if you compute that, you're going to get exactly this quantity, 30.66. Okay. And then the same thing, no? Theta, itong theta, theta, which is theta V minus theta I, is the arctangent of Q total over P total. And this is going to be 15.55 degrees. Okay, if I just, this one divided by this one, you get the arctangent. And since theta V is equal to 0, then theta I will be minus 15.55 degrees. So kung kailangan natin ng phasor value ng I of t now, the phasor is 30.66 at an angle of minus 15.55 degrees amperes. Okay. So I did not have to do any complex power calculation. And sometimes they don't, the problem doesn't really require you to know the angle, no? For example, if I was an electrician, all I wanted to know was, if I'm an electrician, all I want to know is the RMS value of I of t, because I want to know how big a wire I put here. All I need to know is the RMS value of this. So I don't need to know the angle. So dito sa method na to, you can skip this step. No? You can skip this step rather. Kasi dito pa lang, alam mo na yung sagot. 30.66 amperes. Okay, I have another example, but unfortunately, I've run out of time. Okay, so hindi ko ma-discuss tong example na to sa'yo, but anyway, I'll send you these slides, no, and try to solve this by yourself. if you want, you can show me your solution and I can tell you whether you're on the right track or you're not on the right track. Okay? So that's all I have now, no? Because we already ran out of time. Any questions? Okay, if there are no questions, then I'll close the session as soon as either of you leave, or both of you leave rather.
Thank you po.
You're
Thank you
welcome.
so much po. Thank you so much.
Okay, sure.